All right, let's take a stop here and then see what you have for your table so far. What do you have for your table?
We have copper as the strongest.
Copper is the strongest, and the what?
And the what?
The next what? What's below copper that you have?
We were taking, we were
Lead
arguing
too.
copper, but we
Okay.
put zinc as the, so we started strongest
Actually,
with copper.
silver would be.
And zinc was the,
Silver's stronger?
Yeah.
Okay, so you had silver at the top, and then copper?
wait,
Yeah.
Silver ion, right? And then copper too, and then what?
Yeah, then lead.
then lead,
Then lead, okay, and then
zinc.
zinc.
Well, zinc would be at the top, and then HCl would
Wait,
be
it's,
on
the
top.
table is going from weakest to strongest,
Yeah,
but it's okay. It's just,
Oh, weakest to strongest?
yeah. So copper would be at the bottom, and then silver would be on top of
Are they doing the, what, actually, I better take a look at the table. Let me do the table. Unfortunately, that's, normally I don't do this table. Normally I just say forget this table, and we just do the reactions, and I have you do. But this semester I was going to switch it and have you do the table rather than the reactions. But I should have looked at the table more carefully because that table doesn't match. That table doesn't match our books table. That table doesn't match this table in class. This is a whole another flipped arrangement. The table that I'm going to hand out for the test has the strongest oxidizer on the top. And this is the standard table. The standard table has the strongest oxidizer at the top left. 95% of the tables that you see are organized like this. You know, the strongest oxidizer on the top.
just gonna confuse.
Yeah. So we have to invert this table, unfortunately. We have to put the strongest oxidizer on the bottom left, which isn't that. The strongest oxidizer on that table over there is on the bottom right. And so this is a screwed up table. And if I could have my opinion on everything, then everything would be done my way. But this is a democratic department, which means we have to do everything as far as consensus goes. And so for some reason, anyway, let's invert it now. Okay, what's at the top? Zinc 2+. This is going to be the weakest OA. It really doesn't matter. You should have enough flexibility to look at the table anyway. And so this is the third variation of table that we'll see. And so Zn2+ is the weakest. You got the strongest as Ag+, and then
No, our strongest is copper.
your strongest is copper. Okay.
It's Ag, sorry.
Silver ion is the strongest. Silver ion is the strongest. Okay, and then
Copper, and then lead.
lead, and then H+. All right, this is the ranking for the oxidizing agents so far, and this is correct. This is the right ranking because silver should be the strongest. Silver ion should be the strongest. All right, now because of the conjugate relationship, what we're going to do is we're going to do the half reactions here. And so we'll just do Zn2+ plus 2 electrons gives us Zn solid. Okay, that means Zn solid is going to be the strongest reducing agent out of this list. And then we'll do 2H+ plus 2 electrons gives us H2 gas. And so zinc is stronger than hydrogen gas as a reducing agent. Pb2+ plus 2 electrons gives us Pb solid. Copper 2+ plus 2 electrons is going to give us Cu solid. And Ag+ plus 1 electron gives us Ag solid. And so Ag solid turns out to be the weakest of the reducing agents. And so if you take a look at this, you know, I guess that maybe, you know, maybe it was done on purpose, this organization, just so that you don't get hooked into believing that there's only one style of chart. It used to be about, I don't know, 15 years ago, this was the standard. It was, the standard chart was like the activity series, lithium at the top. You guys remember the activity series in Chem 4? If you look at the left side of this chart at the top left, it's the activity series. And so that used to be the standard. And then they switched to the one on the handout, you know, the handout I gave you with fluorine at the top left. Okay. But who knows? Maybe 10 years later, everybody will say, okay, let's can those two charts and let's have this as our standard chart. You never know. You know, then there could be some logic for that. I don't know what it is.
Based on this chart here,
Yeah.
By looking at the cell voltage, H2 is the zero, right? Zero voltage. And how come the PV is more negative?
Okay, the question was about the voltages on the chart. I left the voltages on the chart because that's for Chem 1B. The voltages, okay, the voltages have a specific meaning, but what the zero means is zero does not mean absolute zero.
That's just reference, right?
It's just an arbitrary 0 point. If you're at 0 degrees C, does that mean anything significant? No. Is it possible to go to minus 10 degrees C? At minus 10 degrees C, does everything go backwards in the universe? You know, if you're at plus 10 degrees C, you're like this, going forward. But minus 10 degrees C must mean you're going backwards, right? Is that what it means? Negative? No, it just means you're at a colder temperature than 0 degrees C. 0 has no meaning. The same thing on that chart. 0 is totally meaningless. It's just sea level. That's it. Can you be below sea level? Yeah, you aren't going into a black hole or anything? No. And so those numbers, just because it's negative, just means it's weaker than. And so here, this is 0. Right? Either way you look at it, this is 0. And so we're at negative. It just means it's weaker. It's a weaker oxidizer. And then negative here, it's an even weaker oxidizer. And then negative here, it's an even weaker oxidizer. But it's still an oxidizer. Some people have this idea that when it goes from positive to negative, all of a sudden it switches from an oxidizer to a reducer. It doesn't happen that way. Okay. Anyway, let's discuss more in Chem 1B.
In this chart, why are they using hydronium instead of 2 H pluses?
It's just a matter of preference. Some Chem 4 instructors want everybody to use hydronium because it's more proper, it's more correct. Other Chem 4 instructors couldn't care less if you use hydronium or hydrogen ion. I myself, in Chem 1A, we use strictly hydrogen ion because it's easier to write. You know, really it's hydronium. But in Chem 1B, we use hydronium all the time because we look at hydrolysis reactions. And an acid plus water yields hydronium, a base plus water yields hydroxide. And it's drilled into you in Chem 1B.
Like, what I meant was, like, by looking at the cell voltage, if it's more positive, then this is stronger oxidation agent.
Yes.
So that's why the H is in the plus.
Right.
But that's a minus, but that's a 0. So I think why is it? I wonder why it's split.
What? I'm sorry, can you repeat that?
Because by looking at that H is more positive, then it's going like toward the negative from positive. And H2 is 0. The PV is a negative.
Okay. Sorry, this is positive, this is negative. I'm thinking backwards here. So you're saying these are positive here, then it goes to 0, and then it goes negative?
No, it goes like positive, positive, and negative, 0 and next 0.
Oh,
On the table.
okay, then on the table, oh, right. Did you get a reaction between H plus and lead metal? No? You got no reaction? What should happen is you should have gotten a reaction here. A white precipitate should have formed on the surface. And so the reason is this. There was a reaction here, so that means this is out of place. That's what you're saying. This is out of place. Yeah. That's correct. It turns out that H plus can oxidize lead to form Pb2 plus. But the Pb2 plus that forms reacts with the chloride that's present, and you get a second metathesis reaction, precipitating lead 2 chloride on the surface of your lead metal. And so your lead metal should have went from a dark black color to a white color. You have to give it enough time. I said give these reactions time because some of them take time. But the lead isn't going to disappear. And so this one's out of place. That's why. Actually, this order is not right. Now the order is right. So does that answer your question?
So PD, that things should be in the second top. Right?
Yeah, right. P, it should go Zn2 plus to Pb2 plus to H plus to copper 2 and then silver. All right. There's another thing that popped up, and this is that. Did you see that poll on Piazza about the exam? A lot of people are pushing me to push the exam date back, you know. But there are people who have multiple tests on that Thursday next week, you know, and not just one, but a number. And so what I'm thinking of doing is, you know, I'm afraid of pushing it back because that means it's gonna be compressed to exam 3. So what I could do is, if you guys have a lot of stuff going on next week, what we could do is we could push it back to the week after that. If we push it back to the week after that, then I'm going to make this test worth more points. Maybe 130 points or 150 points. If I make it 100, and then that would make the exam 3. Yeah, I was thinking if I make this 150 points, I'll make exam 3 75 points and exam 4 75 points. And then just put more material on this test. Why? Because there's less time for exam 3 and exam 4. Exam 4 is the week before the final exam. We'll just, the thing is, otherwise I have to leave it on the Tuesday, because it's not fair for people who plan. So we could just leave it on Tuesday and keep it at 100 points. Even if I move it to Thursday, I was thinking of bumping up the points a little bit, because the timing between, it's only going to be 3 weeks from that test to the next test, which is going to be less material. And do you want a lot of points on less material? I don't know. Can
you just split up the test on both days? Lecture in the first half and test on the same thing on Thursday?
Oh yeah, you do split it up? Yeah, I could do that. I could make it 2 tests. One, like two tests, break it up into 2 parts.
We cut down the study.
Yeah, we could do like chemical reactions on Tuesday and then the rest of the stuff on Thursday. You want to do that?
Sure.
But the thing is, you're going to be timed. You're going to have a time limit. I'm not going to give you the full 3 hours on both days, otherwise.
The same problem for the people who have come on Thursday.
No, but it's like half.
No, but half the material, but they have to study too for chemistry.
I'm sorry, what's that? Same problem?
It's the same problem for the people who have tests on Thursday.
Yeah, okay. Yeah, okay. You know, nobody wants 3 tests on one day, you know, and if I move it to Thursday, then people are going to have 3 tests on one day. That's not fair.
We cut down the load, so you had a test, now it's like...
Well, anyway, this will go on forever, so I think, you know, maybe the best is just to leave it on Tuesday.
Yeah.
and then just go, you know. That way I don't have to increase the points. We'll leave the points at 100 points, and we'll just take it from there. So it's at least that's what I'm thinking. Well, we'll talk about it. We still have one more day to talk about it. So this isn't that hard, is that? This is easy, right? Can you turn this in on Thursday next week? All right, next thing, we got to continue with our talk on thermal, chapter 7.
Wait, Professor.
Yeah.
What's the strongest oxidized, like, the example you just did? Will that be on the test too?
What?
Will that be on the test too?
What will be on the test?
The strongest oxidized.
Of course, yes, because this is chapter. This is chapter what we talked about, chemical reactions. This type of stuff is going to be on the test. Right? You have to know the driving force for redox, right? Stronger oxidizer to weaker, stronger reducer to weaker. We've been talking about this for, I don't know, a long time, I think. And so, yes, the answer is everything, basically everything that we've talked about from the last test to now and then some will be on the test. All right, let's talk about chapter 7. Now, we need to talk about work, too. In all the stuff that we've done so far, there was no work involved. Up to now, we haven't had to worry about this. Okay, but now I want to get it more complicated. We're going to worry about work. Okay, we didn't have to worry about work because mixing 50 milliliters of water with 50 milliliters of water, there's no work involved in that, except for you had to mix it. But for from the chemist, from the system's point of view and the surroundings point of view, there was no work involved. Okay, what happens is, when do we have to worry about work? When do we worry about work? We worry about work when delta V, the system, changes. Volume. The system volume changes. If the system volume changes, what happens to the surroundings volume? It changes in the opposite direction. And so delta V of the system is equal to minus delta V of the surrounding. This is secondary. What we just look for is, does the system volume change? Now, what did we define the system as for mixing hot water and cold water? The system was 50 milliliters cold water. Did the volume change? No, there's still 50 milliliters of cold water that warmed up in there in the total of 100 milliliters. Did the surroundings change? No, the surroundings was 50 milliliters hot water, which cooled down, plus the calorimeter, which is the rest of the universe, right? The same thing with the sodium hydroxide. You know, we started off with a certain number of sodium ions and hydroxide ions. Did those ions change? Did the sodium ions grow fatter or skinnier or what? No. Did the hydroxide ions grow bigger or smaller? No. And so in that sense, it didn't change. You know, they're actually, if you want to argue it, because we're going from crystalline to aqueous, it did change a little bit, but that change is so small, we'll ignore it. What about mixing the HCl solution with the NaOH solution? We started with 50 and 50, which adds up to 100, and we end up with 100. And so did you see in all the reactions that we looked at on the board or in the lab, the volume didn't change. And so what we have here is we don't have to worry about work. When we have to worry about work, then there's the full version of the first law of thermodynamics. Let me restate the first law of thermodynamics. That delta E of the system is equal to Q of the system plus W of the system. That is, the change in the energy of the system is going to be the heat gained or lost by the system. If heat is gained, then what sign is Q?
Positive.
Yeah. Or lost, Q would be negative. The heat gained or lost, or the work. Okay, when we say work, work is done by the system. When work is done by the system, we give it a negative sign, but that means it loses energy in doing the work. And so the work would be less than 0. Or on the system. If work is done on the system, then the term is positive. That is, the system gains energy by having work done on it. All right, when we're looking at work, we have lots of different forms of work. You know, what is work? The different forms of work that we deal with, you know, there's electrical work. Electrical work is pushing electrons through a circuit. You know, that requires work to push those electrons through the circuit. Mechanical work. Mechanical work means if you have a lid, you know, the lid weighs something, and to push up the lid requires work. And so mechanical work, like lifting a lid up or moving a lid, is work. What else? You know, sound. Yeah, that would be electrical here. Electrical and magnetism. I mean, they're related. If you generate an electric field, you also generate a magnetic field. If you generate a magnetic field, you also generate a electric. You can't separate those. They're hand in hand. So anyway, mechanical, sound, what else? Heat is different. Heat is this. So we separate it from work, etc. We'll just say. What do you think is most important in chemistry? Electrical, yes. This will be very important in Chem 1B.
Mechanical.
But for us in Chem 1A, mechanical work is going to be the most important. Well, when we think about mechanical work, this is Chem 1A. We call this the natural work of a chemical reaction or process. All right, well, what kind of mechanical work am I talking about? The mechanical work I'm talking about is like inflating a balloon, you know. Example, inflating a balloon. Does it take work to inflate a balloon? Yeah, I mean, if you blow up a balloon, it's going to cost you some energy, right? How much energy does it cost you? Well, let's look at inflating a balloon. The amount of work you have to do is going to cost you a bit of energy depending on how big you blow up the balloon, right? The bigger you blow up the balloon, the more work. And so it's going to depend on delta V. The bigger the delta V, the more work you have to do. What else is it going to depend on? The pressure, yeah. The pressure. If you blow up a balloon at the bottom of a 9-foot swimming pool, is it going to be so easy to blow up? No. or the world's deepest swimming pool, it'd be very hard to blow up a balloon. Bottom. I mean, if you're just blowing at 1 atmosphere. And so it depends on the external pressure. The higher the external pressure you have to fight, the more work you're going to spend in blowing up this balloon. And so the work we could easily calculate. The work is going to be P external delta V. Now we have to keep track of the signs. The signs kill people because the signs, you really have to be very careful in signs because the signs really do mean something significant. And so the problem is this. People are very sloppy with units, so even in dimensional analysis, when you got to keep track of the units, people have a hard enough time. In thermo, they get killed. They get killed because a lot of these things, the units work out, but it's wrong. It's wrong because they're using the wrong equation with the wrong restrictions, and they aren't keeping track of all the other things that go along with this. And so we're going to put in the details. And this is going to be the work of the system. The work of the system is going to equal minus P delta V. Why is it going to be minus P delta V? Because, you blow up a big balloon, it's going to cost you a lot of energy. And we have to add that negative sign there because is the system gaining that energy or is the system losing that energy in blowing up the balloon? Losing. P is always positive. Delta V, if you're blowing it up, is going to be positive. So it's going to be a minus P external delta V. This is delta V of the system, not delta V of the surroundings, because delta V of the surroundings will have the opposite sign. The problem is we don't usually write delta V of the system. We just call it delta V, right? Or we just call it W. And then you got to figure out, are they talking about the system or are they talking about the surroundings? Because they're opposite in sign, too. Okay, so these calculations are easy because what we do is we do this in atmospheres. We do this in liters. And so you look at the units. An atmosphere liter, is that really an energy unit? An atmosphere times a liter is an energy unit. It's a weird energy unit. Like if you had 1 atmosphere liter, how much energy did you just expend or gain? 1 atmosphere liter. Well, it turns out it's about 100 joules worth of energy. Well, how do you figure that out? And so the first thing is we're going to look at a unit conversion here. How do we convert from joules to atmosphere liters? This conversion is super simple because you already have it memorized. Do you know you have it memorized? We use R to convert. And R is a 0.08206 liters atmosphere per moles Kelvin. And we know another value of R. Do you know the thermodynamic R? 8.3145 joules per mole Kelvin. Did you know these two R's are equal? And so all we do is this. We go 8.3145 joules per mole Kelvin. This is just dimensional analysis. 0.08206 liters atmosphere per mole Kelvin. What happens? Moles cancel, Kelvins cancel. That gives me joules per. And how many is it? Can somebody punch it out?
Triple two.
Yeah, 222.
0.3.
Okay. Actually, we only need 4 sig figs for this. That's all we're allowed. Joules per liter atmosphere. What are you talking about, pascals? 101.3 joules per liter atmosphere. And so all this means is if you blew up a 1 liter balloon against an external pressure of 1 atmosphere, how much energy did you just use up? 101.3 joules worth of energy. Makes sense. So now we're going to talk about energy in more detail. You know, I first thing I wanted you to do is just memorize. You know, if we're under constant pressure, what do we use, delta H or delta U? Under constant pressure, delta H or delta U? Delta H. If we're under constant volume, what do we use? Delta U. Good. Once you have that memorized, that's good because then you won't forget. Now we got to talk about why is that the case and what is the difference between delta H and delta U. You know, in Chem 1A, I always ask this. Tell me what exactly is delta H? You know, and nobody can answer it in Chem 1A because in Chem 4 they don't talk about what delta H really is, right? Or do they? Does anybody know the definition of delta H? A lot of people say it's the heat of reaction, but what is delta U then? Not the heat of reaction? You know. And so we need to talk about energy in more detail, a lot more detail. And so let's start off with energy. You know, we have something called the total energy. The total energy is just what it says. It is the, I'm going backwards now. I'm going back to the beginning of the chapter. I skipped this because I didn't want to talk about it at that time.
Sorry, just to clarify my notes, you said delta H was used for constant volume?
No, constant pressure.
And then delta U is constant?
Yeah. Did you know delta H is not valid under constant volume conditions? Did you know that? You think delta H is valid under all conditions, right? That's because that's what you're taught. This is why thermal kills people, because they don't keep track of these things, right? Sometimes it's valid under constant volume conditions, sometimes it's not. So tell me when it's valid under constant volume conditions, tell me when it's not. Think about this, because isn't that's like, how can I tell you? I know, because you know nothing about delta H and delta U, right? How can you tell me? All you know is how to do the calculation, right? But now you're expected to know. You're expected to know when I can use delta H under constant volume conditions and when I cannot. And so it's not that hard, but it's a lot of stuff to keep track of, and it's a lot of places you can make a mistake because people using delta H when it's not valid get the wrong answer, thinking they have the right answer. Right? And so this is the confusing thing about thermo is the equations, they don't write a paragraph explaining when we can use that equation, when we can't. You have to have it all memorized. And so the beginning part of memorization is, oh, delta H, constant pressure, delta U, constant volume. What do we call total energy? We call total energy U. The total energy is all the energy in there. Now, in physics, you take some physics, you'll learn that the total energy is equal to something called the potential energy and the kinetic energy combined. If we know the potential energy and the kinetic energy, then we know the total energy of the system. Well, what does this boil down to in chemistry? Well, kinetic energy is temperature in chemistry. What is potential energy?
Like energy stores.
Energy stored in bonds, other stuff. And so this is called chemical potential energy in chemistry. And so we're always interested in what is the total energy because we want to see the total energy changes. And so let's take a look at some total energy changes. Here. We'll do something common, like the combustion of methane, and look at it from a total energy point of view. When I'm burning this methane here, is this constant volume or constant pressure? This is constant pressure. I would have to burn this in a what to get constant volume? A bomb, right? I'd burn it in the bomb to get constant volume, right? Because, you know, hot gases, what happens with hot gases? They expand, so the bomb has to withstand any kind of pressure increases. When the cool gases, when the hot gases cool, what do? They can contract, and so the bomb has to withstand the contraction, expansion and contraction of the gases, right? And so we're doing this under constant pressure conditions right now. And so that's important to know. And so when I look at a chemical reaction like this, I look at the total energy, U. And I look at the total energy initial, U initial, and then I look at the total energy final. This is a reaction that releases energy, right? So we're going from high energy to low energy, and it's releasing. And so here, the initial is I have methane gas plus 2O2 gas. And the final, I'm going to have CO2 gas and H2O. Now, is the H2O going to be a gas or is it going to be a liquid? Well, that depends on the temperature, right? And so what did the methane and the O2 start off at? At room temp, whatever it is today. What did the CO2 and water end up at? Well, I think it got up to maybe 900 degrees C here. So should I say the CO2 and water at 900 degrees C? No, because what happens? Is the CO2 and water still at 900 degrees C now? No. What do you think the CO2 and water is at now? Room temperature. So what should I write here? Should I write 900 or room temperature? Do you see? I need to write, because this is my system. My system is going to start at room temperature, and my system is going to end at room temperature. I needed to start at room temperature and end at room temperature, because if it didn't, let's say I stopped. I stopped here and I said at 900 degrees C. Have I released all the energy into the surroundings? No. At 900 degrees C, for sure it's a gas. But at room temperature, it's a liquid. Not only is it a gas, these are moving very rapidly. They have lots of kinetic energy. And so if I stop at 900 degrees C, I haven't released all my energy to the surroundings. I need to wait until this is fully cooled down and dissipated all that energy to the surroundings. And so I don't want to stop here. Whenever we're doing anything like this, what is our system? Is our system a reaction or a process? Or, actually, it's a reaction. Is our system an object or? It's a reaction. That should have been pretty easy. But anyway, when the system is a reaction or object, when the system is a reaction or object, T final must equal T initial. Otherwise, we still have kinetic energy that we can release to the surroundings, right? It's still hot. Uh-huh.
It's hard to read.
Okay. Pen is bad. Okay, let me just do this. When the system equals reaction / process, T final must equal T initial. T final must equal T initial. It doesn't have to, right? We could stop midway here, but it's not done. We're stopping midway. And we could do the calculation here, right? But we don't want to. All right. Now let's take a look at delta U here. Delta U, there's an energy release. Delta U is equal to delta EK plus delta PE. Actually, no, I'm sorry, let me go the other way. Delta PE plus delta EK. Here. PE stands for potential energy, EK stands for kinetic energy. And so when we're here, kinetic energy is related to what? Temperature. Did the temperature change? No. Therefore, the average kinetic energy is the same. And so in this case, delta EK is 0, and therefore the only change was in potential energy. In other words, methane and oxygen, you know, if I fill this room up with methane and oxygen, do you feel comfortable? No, you feel uncomfortable because that's high potential energy. Versus if I have a beaker of water and some CO2, you know, hopefully not too much CO2, but not too much CO2, is it okay? Yeah, this is a stable combination. This is a unstable. This is a change, a big change in potential energy, chemical potential energy. Versus objects. When the system is an object, let's take a look at an object like this. When the system is an object, here, H2O liquid. And let's look at the total energy here, U. And let's go from H2O liquid at RT to H2O liquid at 80 degrees C. Would you say H2O liquid at 80 degrees C has a higher energy, total energy, than H2O liquid at room temperature? Yes. Okay. There's got to be a change. There's got to be an increase in total energy. Delta U is equal to the change in potential energy plus the change in kinetic energy. EK, which is called kinetic energy.
So will system objects always have a change in temperature?
Always.
Okay, so that's how you tell the difference.
That's why, yeah, that's why I have you memorize that, those equations, right? Now we're going to talk about these equations in more detail, you know, to get more of the fundamentals of thermodynamics down. Here, water versus water. Any difference in chemical potential energy? No. And so delta PE here is 0. The whole change is in terms of kinetic energy. And so this is why we have two different things. You know, whenever we have an object can either cool down or warm up, right? Because its potential energy can't change. And so the only way it can absorb that is by doing this.
Could you repeat that one time why the changing potential is 0?
Because it's just water. You start off with water, you end up with water. Is water more stable than water, or is water less stable than water?
It's the same.
It's the same, right? Water is the same as water, therefore it's equal in chemical stability. Chemical stability means being attacked by other reagents, you know. That's what I mean. Now, well, water at a higher temperature should be more energetic, meaning, you know, reactions should happen faster, but the reactions are going to still happen either way. You know? Does that make sense?
Yep.
And so we always have a delta T here. When the system is an object, you know, the change in potential energy is 0. When the system is a reaction or process, the change in kinetic energy is 0, therefore the temperature is always the same, initial and final. Because does a system, when the system's a reaction, does the reaction stay around forever, or does it have a finite lifetime? It has a finite lifetime. And so once the reaction's over, then the system's gone. And the system cannot disappear, you know, and secretly sneak out some kinetic energy, can it? No, it can't. And so this is why it starts here and ends here. It might take time, but it's okay. We can wait for that. All right, so that's the change in delta U. Delta U. Now, let's take a look at this particular reaction here. Going back to this, did the system volume change? Was there a delta V? We ask ourselves, what happened to the system's volume? Was there a change in the system volume? So let's go here. You guys memorize the molar volume of the gas at 22.4 liters is STP. What about at RT?
20,
Okay, at ST, 28.8 is too big. Yeah, at RT, the molar, RT in 1 atmosphere, the molar volume of the gas is 24.5 liters. We'll just round it up. I'm going to call it 25 liters. Ready? 25 liters. This is at RT. 25 liters, 1 mole of methane. 2 moles of O2 equals 50 liters. So how many liters initial? About 75 liters. Then we go to CO2. 1 mole of CO2 is 25 liters. 2 moles of H2O liquid. No, liquid. H2O liquid. You should be able to do this. You should be able to do this in your head. How many? 36 milliliters. Good. 36 milliliters. And so we went from 75 liters to 25.036 liters. And so in other words, we lost about 50 liters of volume.
You had to get 75 liters of top. How'd you get 75 liters of top?
3 moles of gas.
Oh.
Each mole of gas is 25 liters. Roughly. You know, these are just crude. We're just looking, was there a change in volume? Yes. There's a big change in volume. That means we have to worry about work. We just don't worry about heat. You know, does all this change in energy? We lose a whole bunch of energy here, right? What happens to all that energy? That energy went into warming up the surroundings. The surroundings is one big object, right? But it didn't just go into warming up the surroundings. Something else happened. That something else that happened was that there was there was work involved. Now we have to dig down deeper and figure out what that work involved is.
How did you get 36 milliliters?
Yeah, each mole of water is 18 grams. So we have 2 moles of water, that's 36 grams. 36 grams is 36 milliliters. That's how. Having the density of water memorized. You got to do some memorization, otherwise you can't do some simple calculations like this in your head rapidly, which you have to do. Think about if you, okay, now I'm going to have to punch it out, PV equals nRT, right? How much time is that going to take? And people are impatient, so, you know, you want to know it sooner. And so you should be able to do rough seat of the pants calculations to see. And to do that, you should have certain key things memorized, like the molar volume of the gas at RT. Forget about STP. STP is kind of useless, and yet a lot of people memorize it. 22.4. How often do you do thermodynamic calculations at 0 degrees C? Never. How often do you do it at 25 degrees C? Take a look at this table. Did you guys read this thing at the bottom of this table? Oh, it's not at this table. Shoot. If you read the bottom of these tables, they say at 25 degrees C. And so that's way more useful. That's why I said memorize this and forget STP. Because we're going to be using it a lot in this chapter, right? Also, we're going to be using, what do you think we're going to be using? Avogadro's law or Dalton's? in this chapter? Actually, maybe both, yeah. We need both. Why do we need both? Because if we do it in the bomb, we're using Daltons. If we do it out in the open, Avogadros, right? Do you guys see? We need that stuff for this chapter. That's why you have to have that down. You have to really understand it. What do you think? I'll tell you, 98% of chemical reactions occur in a bomb or occur in the open. In the open. So what do you think you're going to be using a lot more of? Avogadros or Daltons? Avogadros. Totally Avogadros. Yet in Chem 4, they gave 0.5% of the time to Avogadros, 99.5% of the time to Daltons. Why? Because Dalton's so easy. Well, actually, both are easy. I don't know why. It should have been at least 50-50 in Chem 4, right?
Yeah.
Otherwise, this is much more of a struggle if you only know Dalton's law and you know it well.
I really weekly one of Avogadros more.
Oh, did you? Oh,
Yeah.
good. Good. That shows some foresight into this. Let me tell you, thermo is not an easy topic because, all of a sudden we got to keep track of potential energy, kinetic energy, all this other stuff. And then it grows bigger and bigger and you get more and more symbols, right? And so it becomes quite complicated. And, it becomes so complicated that at UCLA they have bumper stickers that they made that say, I passed P-Chem. P-Chem stands for physical chemistry, which the first part, the first quarter of physical chemistry is all thermodynamics. The hardest is the first, and then it gets easier if you take a year of P-Chem. And because the failure rate is so high, In fact, I was searching this because I was looking for something, and I saw this debate, and I ran across it on the internet, and there's a debate at Harvard between the students there. What is harder, P-Chem or organic? And so there are arguments on both. A lot of people think P-Chem's harder than organic. And why is it harder? Because, people I don't need to know that. I don't need to memorize this, I can slide by. You can't slide by. In P-Chem, unfortunately, if you don't know this Avogadros, Daltons, then you aren't going to pass the course, You have to know everything because everything else relies on that. Whereas in Chem 1A, thermo, I'll take the hit. I'll slide by. You can slide by in Chem 1A without knowing thermo, right? Because there's so much other stuff.
And thermo is going to...
Yeah.
Never mind.
And so the point is, start memorizing some of this stuff, and it's not hard because it's not you have to be a genius to pass P-Chem. All it is repetition. People look at it once and they think they know it. And maybe some people can, but most people can't. And that's why a lot of people fail that class because they look at it once and no, it doesn't stick. One time it never sticks. Work, Minus 23 joules, what does that mean? Well, it means what? Is that minus 23 joules for the system? Is it minus 23 joules for the surroundings? Minus 23 joules for the system means the system lost 23 joules. That means the surroundings must have gained 23 joules, so it'd be plus 23 joules for the surroundings, right? You got to be able to do this, otherwise you get all mixed up and things get, difficult. And so thermo, at least at the lower levels of thermo, is not hard as long as you keep drilling it, and then you'll get it. And so you can pass P-Chem too. Get a bumper sticker. Although you have to pay for the bumper sticker. Somebody gave me it because I mentioned it. I mention this every semester. So one of my past students who transferred to UCLA bought one of those bumper stickers. I have it in my office. I haven't put it on my car though. It'd be embarrassing. But I've seen them around once in a while. So anyway, we have to now deal with work. And so this is what the first law is. let me write the first law using our symbol. Delta E is not the symbol we're going to use. E stands for energy, right? But our book doesn't use E. Some books use E. Our book uses U for energy. And so the first law of thermodynamics is delta U is equal to Q plus W. And this is how it's written. But you should know that, you know, if this is for the system, then you write system, system, system. If this is for the surroundings, you'd write surroundings, 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 right? And then you know about the sign convention. And so we can figure that out. And so we know that delta U is equal to Q plus W, so this is equal to Q plus W. So the question is, how much heat are we going to get from this? Burning methane. Right? Well, the amount of heat we get is dependent on how much work is done. And how many different types of work are there? There's lots, right? For example, what was one type of work? Electrical work. And so do you know that there's something called a methane fuel cell car that burns methane? You don't see any flames, but it burns methane and converts that energy into electrical work. Have you ever seen those methane fuel cell cars? And then there's those CNG cars. There's CNG cars that burn methane and convert that into work, mechanical work, right? And so how much heat we get depends on how much and what type of work is done. And so we need something else. We need to know about state functions versus what? If it's not a state function, then it's what? Have you heard the term state function before? No. Okay, there's two things. There's going to be state function versus path-dependent function. Delta U is what we call a state function. Q and W are path-dependent functions. And so we could use the mountain analogy that's used in the book for this. You know, if I climb a mountain, let's say there's a certain elevation here. Say it's 3,000 feet. How much work is it going to require to climb a 3,000-foot mountain? Well, it depends on the route, on the path. And so in terms of physics, we can do this. You know, there's a difference in energy here. And the amount of work that should be required is based on this. It's fixed. The work is going to equal mgh. You know, how heavy is the mass? You're fighting against the force of gravity, and how high are you pulling up the mass? mgh. Have you heard of that? But we know that, okay, let's say we calculate that, but you know, this is what we would call the minimum amount of work. You know, you can't go under this because, you know, but in order to climb this, it depends on the path. Maybe it's an easy walk up, or maybe it's a very steep climb, you know? And so the amount of work depends on the path you take. And so this is the energy. We'll just call this delta U here. Sorry, not the work. Delta U. Delta U is equal to mgh, which is equal to Q plus W. And so, well, actually we could, this isn't a great example because we could end up taking a lot more. Actually, no, I shouldn't write this like this. You could end up using a lot more. Let me eliminate that. And so it depends on the path. And so the amount of work that we do depends on this. So let's do a couple of simple examples first here. let's burn the methane in a bomb. Delta U, whether we burn it in the bomb or burn it in open air or whatever we do, is always the same. Delta U just depends on the initial and final states. It is path independent. The path our path we might take is a bomb, or burn it on top of Everest, or etc. And so it just depends on the initial and the final states. It is path independent. Q and W depend on the path. For example, bomb versus some other path.
Oh,
So we do this like this. Delta U is equal to Q plus W. Now how much work is done? And so we got to think, what kinds of work are there? Did we generate any electricity doing this? Like in a methane fuel cell car? We didn't generate any electricity. Pretty much the only thing we did was, did we do any mechanical work, like pushing up a piston or lifting a lid? Maybe there's some sound, but it's negligible amount of work. Maybe there's some light, but we'll factor that in. And so when we do this in a bomb, how much work did we do? We did no work. And therefore, all that energy is converted into heat. However, the more work we do, the less heat we get. And so this is like this. Okay, you're on a slide at the top of the slide, and then you're going to go to the bottom of the slide. And so that we got a delta U here. Delta U is equal to Q plus W. So we're going from here down to here. We're losing energy, right? We can lose energy in the form of heat or in the form of work or both. If we slide down this, what's going to happen to your butt? It's going to start to warm up, right? Because of all the friction. And so in other words, we convert all this into heat. Was any work done? No. And so basically, actually I should have used a different color. We get heat, Q. And the slide is going to warm up, right? We're going to get some heat. All right, the other option is you put some frictionless, you just put some oil. Let's oil this slide up. And then we're going to tie a rope around our waist. And then we're going to attach this to a frictionless pulley here. And then we're going to have a weight. This weight is going to be an equal mass in terms of body weight here. And then we're going to go down the slide. If these two masses are about equal, what's going to happen? Nothing, but let's just go down little by little, infinitesimally slow. And then what happens is, how much frictional heat are we going to generate? Nothing, and we're going to convert all this into work. And so in this case, Q, we can get the 0 and have it all as work. Well, you know, when we burn methane, we're very interested in how much heat is evolved because we can use that heat to warm up our tea or coffee, right? Or cook things. And so probably the best way to warm up your cup of coffee, to use the energy most efficiently, is to burn it in a bomb. But unfortunately, the bomb is not practical, right, for heating up. And so are we going to lose heat by burning it out here because we have to do work? No. Do you know what? We're actually going to gain heat by burning it out here. How can we gain heat? In fact, you know, it would be dumb to burn it in the bomb if we're trying to heat something up, because we'd get more heat by burning it out here in the lab than burning it in the bomb. So how could we get more heat? Isn't this the maximum amount of heat we could get? Yes or no? I mean, if we do 0 work, this has got to be the max. No, we maxed out the potential. There's no more potential we can max out unless water decomposes or CO2 decomposes into something more stable. But it doesn't. There's no more potential. We're maxed out in the potential. There is more potential energy, but we can't harness it. You know, there's more potential energy in the bonds and everything else. We'll talk about that in more detail later. But basically, where are we getting this extra heat from? Do you know? The surroundings, because we have to see what's happening with the surroundings as well. And so we're going to look at that next time. But let me talk about one thing really quick, and that is, what is delta U? Delta U is U final minus U initial. This is called a change. These are called absolute. And chemists don't call it total energy. We call it internal energy. This is absolute internal energy. And absolute internal energy is the total energy. So what does the absolute internal energy consist of? Kinetic energy, temperature, right, and potential energy. Now what is potential energy? And so this would be equal to Q final plus W, what is it? No, actually, let's not go there. U absolute would be equal to PE final plus EK final minus PE initial plus EK initial. That would be it. The kinetic energy is easy. The potential energy is difficult. This is an easy calc. This is a very difficult calculation. You know, what is the absolute potential energy of a beaker of water at 25 degrees C? And so if I had a beaker of water at 25 degrees C, let's say 50 grams of it, what is the total energy inside that water? Well, 25 degrees C is easy because we have an equation, we can calculate the kinetic energy. But what is the potential energy in there? That's harder. There is potential energy in there, but we aren't actually going to calculate it because the calculation is too difficult, because we have to calculate the bond energies. Well, that's easy. We have to calculate how much energy it takes off to pluck the electrons off. That's not so hard. We have to figure out how much energy is contained in the nucleus. So we've got to destroy the nucleus, break it up into protons and neutrons. That's not so hard. Then we've got to figure out how much energy is stored in a proton. So we've got to break up the proton into smaller bits and pieces. That's hard, right? People are trying to do that. And the electrons, do the electrons break up into smaller bits and pieces? Do the neutrons break up into smaller bits and pieces? You know, how far can we break it down to see how much total energy is stored in a water molecule? Do you see that calculation is very difficult? All right, we're going to stop here and then